Hi, my name is Nick Fitzke, and I'm a professor in the Department of Chemistry at Mississippi State University. You are currently watching the second of a three-part series on processing and inspecting simple NMR spectra in a Linux environment using programs like NMRPipe, Sparky, and Pokey. If you haven't watched the first video, I encourage you to do it in the description below. And you'll find there also the sample data files and the scripts that we're going to be using in these videos. In part 2, this part, we examine how to process NMR spectra, what to look for when you're phasing, and how to interpret NMRPipe processing scripts. I hope you find the video useful, but I need to include a few disclaimers first. First, this video isn't tailored to the environment that we have here at MSU. It might not match what you have. I hope you find it useful, but there might be some differences and you'll have to watch out for those. Second, if your advisor or PI wants you to do something differently than what I'm doing, you should do that. There are a lot of ways to process NMR data, to store NMR data on local computers, and my way might not be the best. In fact, probably it's not the best, and you should do what your PI tells you to do. Finally, this video was recorded as a discussion between me and a graduate student. He's a brand new graduate student in my lab, and I hope it's very helpful to you. However, the production quality might not be up to standards that you might be used to from other channels and even from this channel. Like I said though, I hope it's still helpful and that you can learn something from it. With that out of the way, let's get on to the video. I hope you enjoy it. Okay, so in the last video, we talked about all of the NMR stuff and sort of what goes into an NMR spectrum, how do you copy it to your computer, what some of the things you want to be looking at and looking for. And so this one in this video we're going to talk about processing using NMRPipe. And so again, for our lab we have a video or a standard processing script that serves as a good baseline for two-dimensional spectra, here called 2D save FT. And so if we open that again with Xemacs, we type the name of the file, and then we remember to put our ampersand at the end. Again, that brings us back to let's just use the command line again, which is important, right? Because we want to be able to type into this window. But it also gets us the Emacs or Xemacs text editor. Just for curiosity, if you ever forget that ampersand, right? And you're sitting here and you're typing, and then all of a sudden you go back here and you're trying, hey, where's my text? I can't type any commands. So you can always do Control Z, and then notice that will stop Xemacs. And if you go in here and now you try to type something, you're not going to be able to type into this window, right? But you can then put Xemacs in but you do have access to your command line again, and you can put Xemacs in the background by clicking here and typing BG, and now all those keys I had typed, came through. So the faster you remember that, the better it is. Otherwise, you might have some fixing to do. But then from within here, again, I think most of the lab computers are configured so that this doesn't happen. But if you do get this weird bottom window, just click into the top window, Control X, and then 1. Okay, so, and then our normal workflow is run fid.com. And once that runs, you don't have to keep running it again, because that basically creates the FID files that you can then process. But then you can then run this processing script as many times as you need. And so it's already been run, but when we run it, just note, for the verbose commands, it usually writes out the last commands that it runs. So up here, the last command that's being run is phase correction. So there's a PS, and it's telling you that it's so fast that you don't really see it, but if you run it again, you can see it sort of count through. And then the bottom down here is the mult. And so again, So here it makes sense, right? Phase cycling, it should go through 128 because we've got 128 proton spectrum to look at. Now you might say, well, why is it doing five? Why does that become 512? Well, we'll get into a little bit of this, but the zero filling basically adds a whole bunch of zeros at the end, and so if you start with 128, or in this case 64 complex points, and you zero fill it 3 times, well, 64 doubled. You know, every zero filling amount or unit is usually doubling the amount of points you get. So in this spectrum, I'm zero filling the proton dimension 3 times. So I would double it once, which would take me to 160. So it takes 64 complex to 128 complex. Double it twice, which takes me to 256 complex, and then double it 3 times, and that would take me to 512 complex. And so if I doubled it 4 times, and let's just try it, right? There's nothing wrong. The script is not set in stone. You can always edit it and run it again. Hopefully that goes up to, no, never mind. It's still 120, it's still 512. It might be reporting the proton, or the nitrogen, and not the proton. Oh yeah, of course it is, because yeah. So this would be zero filling in the proton dimension, and so we need to zero whereas this is reporting the number of nitrogen FIDs, right? So again, we collect 128 FIDs, each corresponding to the nitrogen frequency that we're trying to measure, and so if I change this to 4, that will, now it's 1024. So zero filling is actually really important for some of the quantitative NMR that we do. And so you want as many peaks or points in each peak so that you can make sure that you're really picking the maximum that represents the amount of NMR signal. But 3 is usually a pretty reasonable size. Since we're talking about the zero filling, so -ZF means double your data size 3 times, and then auto means round up to the next power of 2. And so for some technical reasons, the Fourier transform that's used needs to operate on a power of 2 number of data points. So that means 16, 32, 64, and so forth. And so this auto will make sure that your final number of points is always a power of 2, which will speed up the Fourier transform. And again, since we're, well, let's take a brief hiatus from talking about zero fill, and let's look at the phasing, which I think is important. So again, if I go into NMR draw, that will bring up the spectrum, and again, this negative positive sign that you're seeing in the horizontal axis, that just reflects bad phasing. And if I put in if I type H, so lowercase h, I get that horizontal slice through the spectrum, and you can see that the peaks are mostly negative, but there's a little bit of a positive hump, and so that's what you're seeing here. Typically the way I like to start is just pick a very intense peak and get that phased so that I like it, right? And so I can, drag on this P0, which is 0 order phasing, and you can see that's sort of putting the peak through the paces of something that's positive, absorptive, dispersive, right? So this is called a dispersive line shape. Negative absorptive, and then a dispersive in the opposite phase. And so again, we're going to try to get our peak here to be positive, and you can do that just by clicking on that slider. You can also do it by clicking to the left and to the right of the slider, and so you can see as I click, I'm moving it in a smaller amount. And then there's this little slider that's the same thing, but it's the fine mode. And so again, I can click to the left of that and to the right, and it's doing really, really small phasing amounts, or I could click on this and do a fine-tune adjustment on the phase. And so, it's kind of a, eyeballing thing here. A couple of other notes is that within the, NMRPipe doesn't make this obvious, but the title window is telling you what the mouse buttons do, right? And so inside, I get select, pan, zoom, and really pan and zoom. Select isn't going to do anything here, but if I had peaks, I could select peaks on this spectrum. But then I could also zoom in on a peak, and so if I right click and then sort of zoom in, you can see I'm zooming in horizontally. I can also, once I've zoomed in a little bit, I can press the middle mouse button and pan left and right, although again it's not doing a ton because this is pretty broad zoom in range. But then oftentimes what you really care about is what happens when you click outside of the spectrum. And so outside of the spectrum we'll get to phase pivot, which we'll talk about in a second. But then the middle mouse button, if I click and drag up, I can scale the spectrum. And so if I'm really trying to look like, is this phased, I should have a pretty even baseline on the left and the right hand side of the peak. And so sometimes zooming in or scaling up, as NMR Draw calls it, is helpful to look at that. And then I can also adjust the offset, which just shifts the position of that horizontal slice that I'm looking at. So those are what the mouse buttons are doing, and they change from time to time. So you got to keep an eye on them if you're in a different mode. But here, this looks like a pretty reasonable phase, and so P0 of 149.2 is what I want to look at. We didn't do any first order phasing, but we're not going to do that right now. Again, we're just trying zero order phasing, again, on one of the more intense peaks. And what's important to remember is that 149.2 is the difference between where you started and where you ended up to get this degree of phasing. And so 149.2, I'll remember that. And if I look here, again, I'm phasing proton, so that means I would want to worry about this line. So phase correction, zero order, and my starting point in this case was minus 131.4. So this is why I always like to have a calculator. If I do minus 131.4 plus 149 plus 149.2, so positive and negative matters, I get a final value of 17.8. And so I'm just going to delete that, and now I'll write 17.8. And again, within Emacs, you can save it. Just click on the save. I often use the keyboard commands, which is Control X, Control S will also save. But now, notice if I go back to NMRPipe, if I click on my window, or NMR Draw, nothing has changed, right? So I have to rerun the processing script and reload the data for me to see the effects of that change. And so that's why it's helpful here to have access to your command line. And so notice I forgot to type the ampersand, and so once again I'm just going to do Control Z and then type BG, and now I can do this again. So /2D standard. And so now it runs through the processing script, and if I go in here, again, it's still not the same. I have to type lowercase r to reload the spectrum. And so now this is what we want to see. This is peaks that are in phase in the horizontal dimension. They appear to be in phase in the vertical dimension. And for an HSQC, you rarely have to use first order phasing for this kind of a spectrum. It's actually a really nice HSQC. And so I'm going to click up here, this minus sign. If I hit Shift T, that automatically sets the bottom level of the contour to be where it thinks the noise is. And so that's actually pretty decent. I'd say that's pretty good, actually. And so you're seeing, flecks of little bits of noise here and there. You're also seeing some truncation artifacts. So we've truncated the oscillations pretty early, and so you see a little bit of sync wiggles on the left and right. That's all that is. Don't worry about that. But if I look and if I click on this minus sign, I can continue to go into the noise. And so you can see I go lower and lower into the noise, and I get more of these extra sort of spurious peaks. But as I look into the noise, I'm not seeing that there's a trend one way or the other. So all of these peaks look roughly symmetric to the left and to the right. You can see that it's there's not a particularly strong bias for all the peaks to have a little bit of phasing off in the left side or the right side. And similarly in the the vertical axis, I don't see that the top is always more positive than the bottom, and vice versa. So that's telling me that my phase is pretty decent. Now, if I wanted to do first order phasing, again, I would use I would have to go into my phase mode. So I'd have to go either H to do horizontal or V to do a vertical slice. And occasionally you'll do like a first order phasing in the horizontal dimension, where you might click here and go and see, now that I'm clicking with my left mouse button, I get these arrows, and so this is specifying my phase pivot. And so if I get this peak, which I have selected in phase, and I move my phase pivot to the middle of that peak, now if I drag the first order phasing, what's going to happen is that the phase of this peak should stay the same, or the region surrounding the phase pivots will stay the same. But now if I look at peaks that are farther away, they actually start going dispersive and absorptive. And so I'm applying a linear phase correction, where the phase correction is 0 here, but it gradually increases as I get linearly farther away. And that can be really clear if I type A, lowercase a, and then I type H again, lowercase h, and now I have a second window. And so you can see, if I drag my first order phase correction here, again, the peak over here around 10.5 ppm, that's not changing. But the peak that's a little bit farther away, this peak is now becoming more dispersive, and this peak has become really dispersive. And so you can think, again, the phase correction is increasing as you go from the left to the right. But again, we don't need to do that here, because all of the peaks are pretty much the same, and so and that's really what you're aiming for. However, if you have a very broad range of chemical shifts, you might need to use a little first order phase correction. So I can type lowercase e to get all this out and exit out of this. I can type Shift T and now bring my my noise up. And then one thing that students will often do that sometimes, well, depending on my mood, can annoy me. They'll look at a spectrum and they'll put the contour limit or the contour floor way up, so it's like, oh look, this is perfectly phased. But then if I go back and look at the actual noise, you can tell that, oh no, you're just hiding all the negative peaks that are at the right hand side of your peaks. So yeah, when you're phasing, it's always a good idea to go as close to the noise as you can bear. And again, for me, that's, this stuff here, this isn't noise. This is real spectral features. We don't like them because it's truncation artifacts. So it's artifacts, but it's not noise. This stuff that we're seeing, these random flecks, right, that represents real noise, and that's where you're starting to look at the noise of the spectrum. Okay. And you can always interrupt this by just clicking in there and then just redrawing it. And if you're not happy with the first bit and you're sick of waiting, you just keep doing that until you are happy. So, but this is fine. Again, I'm convinced that this is in phase. And so we don't need to look at all that noise, particularly if we're doing like an assignment project. So, and it does save some time because it takes less time to regenerate. So again, so horizontal mode lets us look through the horizontal slices. Vertical mode lets us look, so this is lowercase v, lets you look through vertical slices. You can also do B for both, and so now you can look at both the horizontal and the vertical slices, and so it drags around. You can type lowercase l for location, and that lets you sort of like, if you really want to pick out a peak and find out where it is, you can dig in that way. And then the final thing maybe to note here is that if we look up here and click these little up and down arrows, this is a way, like if you're bad, like sometimes I am, where you can't click really close and you want to sort of really dial in, you can use these up and down arrows to sort of move it. And you can see that the peak is moving to the right in this case, and if I click back, it's moving back to the left. And that works for the up and down as well. And this will move you up and down 1 point. And so, again, now our y-axis here is ppm, right? So we don't see the number of points. But the zero filling we did means that we have 100 or in this case, I guess 512 complex points that represent each of these peaks. And so when I hit, exit out of both of those and then hit horizontal. When I hit here and I go up and down in my y-axis, you can see it's moving up. And if I were to click this 512 times, I would go from all the way at the top to all the way at the bottom. Okay. Another nice feature is zoom. And so I can, now zoom brings up this zoom box. And again, this is a Frank Delaglio user interface decision. It's not like you would typically zoom, where you would just drag and it zooms. This is actually a little bit nicer, I think. Whereas if you click the middle mouse button, you can drag the position of the center of the box. And so, like for example, if I want to zoom, let's zoom on something a little bit more interesting. Let's zoom on this triplet of peaks. And so I can click here, and now if I left click over here, I can move my window up my upper corner or my lower corner. All right, so I can click on the four corners as I want to determine where I want to look, and then again, if I right click inside the box, I get to zoom, and if I left click outside the box or outside the spectrum, I exit the zoom mode. So again, if I'm centering, oops, I don't know what I did there. I think I used my mouse scroll wheel, and that adjusted the noise a little bit. But anyway, so I right click here, or I center click, and then I just sort of select those three peaks, and then right click in the spectrum. Now I zoom in. And you can see, so looking at this, I can tell our zero filling is really nice. All of these lines are nice and smooth, right? The contours are you can tell there's a little bit of pointedness, but the contours are smoothly dispersed. You get a nice picture of all three peaks. Actually, this is 5 peaks because this is 2 peaks, this is 2 peaks, and this is 1. But in this case, now you can zoom in, and if I type lowercase e, I exit out of that mode. But since we had talked about zero filling, let's think about, again, since I'm resizing the window, I kind of have to go in and hit R. And it doesn't, again, on the hard systems, it'll work fine. On my virtual system, it doesn't always like resize. So I'm kind of stuck with this. But let's go back and change our zero fill and just see what that looks like. All right, so here I'm going to change my proton zero filling. I'm just going to do zero filling of 1. And then go back in here, rerun that processing script, and then open up my spectrum. I'm going to redraw it. Now again, unfortunately it zooms out to everything, but it's pretty easy to zoom back in. And we'll see how this looks. Okay, so notice that you're starting, now in the contours you're not actually seeing a big difference. But notice that you're starting to see a little bit of blockiness here, right? And if I put myself, if I type exit and put myself in horizontal mode, right, if I look at that peak, you can definitely tell there's, that is not a smooth peak. And if I were trying to estimate the maximum of this peak, probably if I were to put a smooth curve through all these points, probably the maximum is like here. But the maximum value I would actually get would either be this or this, because that's what's actually in the data. And so that shows up, for all of these. But notice that if I go to vertical mode, right, this still looks pretty smooth, right? I mean, there's a little bit of difference there, but for most of these peaks, it's actually pretty smooth. Notice also that my horizontal line is jumping, right? Because that's jumping from the actual points, and so I don't have a nice smooth x-axis anymore. I have a very discrete x-axis, and I can make it worse by going into, let's bring both of them down to 0 fill 1. Actually, well, let's put this back. Let's change this to 3 again, and so now we're 0 filling 1 time in the nitrogen dimension, and 0 filling 3 times in the proton. Let's see what the effect is. Again, we've got to reload, and again zoom. Okay, so nitrogen, it's actually much worse, right? Because we're collecting so many fewer points to begin with, and so if I look here, these are not nice peaks. I mean, they're peaks. They represent what's actually there, but this peak really only has one value, sort of representing the maximum. Whereas if now, look back in proton where we set it to what it was before, it's nice and smooth again. Right, so 0 filling is really, what we say is the 0 filling affects the digital resolution of the peaks. It doesn't make it narrower, right? The actual splitting between the peaks is not really changing, but it does affect the number of points that sample a peak and make it smooth or rough. And so, okay. So we've looked at, we've looked at the Fourier transform. We've looked at phasing. So FT is Fourier transform. Usually you don't need a whole lot of parameters there. Extract is pretty much self-evident. Like, where do you want the peaks? And since we're in the proton dimension here, we're extracting from 6 ppm to 11 ppm in proton. You could do the same thing in nitrogen, but you often don't need to because the nitrogen sweep width defines the region of interest. For nitrogen, again, oftentimes it's very rare, well, it should be rare, that you have a nitrogen phasing that you really need to adjust. Generally speaking, the 0 order phasing for nitrogen, for the nitrogen dimension, should be either 0 degrees, 90 degrees, or minus 90 degrees. And the first order phasing should either be 0 or minus 180, right? And the reason I say that is because this is defined really by the pulse program itself, right? The direct detect dimension, the proton dimension, you always have a little bit of uncertainty in where you start acquiring the data. But the nitrogen dimension, if the pulse program is written properly, it should be very clear that you need 0 phasing or 90 degree phasing, and particularly the first order phasing should almost always be 0 or minus 180. And so a lot of times you'll see, or maybe sometimes plus 180, I forget, the sign is different in topspin versus NMR draw. But if I do like minus 90 plus 180, and I save that and now look at it, again, that's a very common value that you would use. It's not correct for this spectrum, but if I reload, now you can see now you can see we have, yeah. So this stuff down here at the bottom, that actually is in phase. It's negative, but it's in phase. This stuff here at the top is also in phase, but it's positive, or mostly in phase. And then it sort of makes this transition between the two. And so clearly this is the wrong value for this spectrum, but it is the correct value for some spectra. And the other thing that you need to worry about is if we go here. Now again, it's the wrong value for this spectrum, but notice that you get these weird streaks. Right? So I have all this, this is not just being in phase. Like down here, I'm getting these massive streaks in the positive and negative dimension, whereas here, the streaks are much less. And so one thing to keep in mind here, and I'm not going to wait for it to draw all that, is that if you do have phasing that's minus 90, 180 in the nitrogen dimension, then this coefficient needs to be changed from 0.5 to 1. So again, for some technical stuff that we're not going to get into here, this dash C represents the multiplicative factor for the very first point in the FID. And to get good baselines, you want that to be 0.5 if you have zero first order phasing, and 1 if you have 180 degrees first order phasing. And so again, that's really the only time you would need to change this dash C. And since we don't have 180 degree first order phasing in the nitrogen dimension, we're going to reset that back to what we started with. So now we should get back our... And again, I'll work with you to sort of show you when that's needed or not. And there's some good papers. I think Stefan Zizek was the author of the paper I usually send you guys. It's an add-backs paper. Again, it gets into the technical weeds, but it's mostly a Fourier transform thing. It's not really fundamentally an NMR issue. But now if we go here, we reload, we should see our normal peaks again. And again, everything looks good here. Like the baselines, yes, we have some of these oscillations from truncation on the left and the right, but the baselines look flat. The peaks look like they're well organized. And maybe in a future video we might talk about how you might change the apodization, right? So this is a sine bell multiplication. This is a sine squared, right? So both of these are SP for sine multiplication. And then the power 2 here means that this is sine squared. The power 1 means this is just sine. And then the ending value is 0.99. And so this sort of specifies where you start and end in the phasing, or in the apodization. So this starts midway through a sine wave, and so it starts high and then ends close to 0. And then this starts high and it ends close to 0, but it scales down as a pure sine, whereas this one is sine squared. Don't worry about that for now. Again, if you take, well, you should take my NMR class. You will take my NMR class eventually, but we can talk about and look at those differences here. Most of the time, for just general looking at spectra, you can leave these alone. And so I think that is pretty much what we need to do for phasing. Again, in some cases you might need to phase in the vertical dimension, right? And so most of the time it's just going to be 90, 180, and in some cases you've got to change it to something different. But if you press H, I mean, now you can phase this exactly like you did the horizontal, or you can, if you press V, you can phase the vertical dimension exactly like you did with the horizontal dimension. And so, but I think that the main takeaway is that, yes, this is a recommendation, but it doesn't have to be, set in stone, right? You can feel free to change things, and as you get better and better at NMR, you should be able to change things. You say, oh, I want a little bit better resolution, so I'm going to change my apodization, or I'm going to change my window function that gets multiplied. Let's see, what else can we maybe talk about here that might be instructive before we move on? Well, I think, yeah. Okay. So one thing to look at before we end, and I think we'll end after this and take another quick break. But if I do type NMRPipe, actually two things, and I type -help, and I want help on a particular function. So suppose I'm thinking about, there's a baseline correction I'd like to do, and so if I type function poly. So NMRPipe -help fn poly, it gives me all of the options that I would need for that, right? And so you can sort of see, this is where we say, okay, well, this is where we're going to start. Like, this is the beginning point. Or I guess sets the range for polynomial baseline subtraction. I can set the order, right? The polynomial baseline. So if I set it to 0, all it's going to do is subtract out a constant. If it's a first order, it's going to do a linear baseline correction. I can do quadratic and so forth. I don't do a lot of this stuff with this, but if I wanted to say I want to do auto polynomial baseline correction, and I want to limit myself to a quadratic fit, I can say auto-ord2, and again, if I run this and then reload the spectrum, it's not going to change because our baseline was really good to begin with. But you can, if you do notice trends in the baseline, you can fix that here. But the more important thing to notice is that, any of these, like if I'm curious about sign bell apodization or sign multiplication, I type fnsp, and it gives me my sign window options, and so I can see what all of these are doing. So again, off is the sign start times pi, so in degrees, and then end is my end degrees, and then so again, 0.5 to 1 represents a quarter of a window. So the last thing I want to mention is in the previous video I mentioned that this pipe focuses on taking the output from the command on the left and pushing it into the command on the right. Since these are all on multiple lines, we need one little trick, and that's what this backslash is doing here. The backslash tells Unix that when you interpret this command, ignore the next character, right? And so in this case, backslash, and then if you look, there's, notice the cursor switches a little bit. This is the end of the line. So what this backslash means is it says, ignore the end of the line and continue processing from the next line. And that's important because sometimes in these processing scripts you'll accidentally type a space, and if I move on it looks exactly the same, but if I save it, it's going to give me all sorts of error messages, right? And so it's like now it's gotten better, right? It's like, look for a trailing space after a continuation, right? But if I have that space here, and again, it might get worse if I put it down here in the middle of the processing script. Yeah, so now I'm getting a ton of error messages, right? Now it still gives me this at the very top, but I have to scroll up to see it. But when I put a space here, what that's telling is it ignores the space, and then it continues with a new line. When it hits the new line, it says, "Oh, you must be done." So I'm going to start running that command you just typed, and so that's why it gives you an error. You need this to be the last character at the end of every line, and if that's the case, these can be all over the place, right? They don't have to be all perfectly aligned. Sometimes I think it's nice to do that, and if you look at the original version, it has them all aligned, but they don't have to be aligned. All that's doing is telling the Unix command line processor, hey, don't finish at this new line, just ignore it and continue on to the next line. So, I think that pretty much takes care of processing an NMR pipe, at least the basics. I mean, you should be enough to be dangerous at this point. And I think, again, from this script writes out a UCSF file. So in the next video, we'll look at how you open these in Pokey and how you open them in Sparky, and how you might copy assignments from one thing to another, and sort of our basic tutorial on Pokey and Sparky. So yeah, we'll hit that in the next video.